So one of the critical things with momentum was remembering how important direction is, right? So if you got an object that's going, to the right, it's important to set up, what's positive, what's negative, especially, dealing with momentum as compared to energy, you've got to have the direction. So impulse is the change in momentum, and it takes a force over a period of time to change the momentum of a system. And remember, delta P, change in momentum, really is impulse. That's what it is. Now, when Newton was describing motion and what was going on, he actually talked about it really in this term and not F equals ma. We get F equals ma from this. So you'll need to be able to derive this as well. If we had, we have, change in momentum is a force times time. Change in momentum is mv final minus mv initial equals force times time. So if we divide both sides by time, we get force to be equal to mv final minus mv initial over time. And if we factor out mass, we get F equals m v final minus v initial over time. And then that's acceleration, ma. So it takes a force over a period of time to change the momentum of an object. And so that's critical there. So we have a bowling ball that's rolled towards a concrete wall at 5 meters per second. Mass is 25 kilograms, hits and bounces back at 3. What is the change in momentum? In other words, what is the impulse? And then the second part, if the impact took 0.62 seconds, what's the force of the wall on the ball? So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so mv final, the final velocity is 3. Hopefully you paid attention to that hint there, very important there. So it bounces back at -3. It was going at +5 when it hits the wall. And so the change in momentum is -200 kilogram-meters per second. And if you use just regular 3, +3, what that means is it was going 5 and then it blew through the wall and is going slower now, which is very different than hitting the wall and bouncing back. The force that it would take to do that, 0.62 seconds, is -322.58 newtons as it goes back. And so, so that's a negative force. The force is this way. And there we go with that. All right, now I want you to consider what would happen if there was like a cushion there, the ball hit and then bounced back at -3. Everything else is the same, but the time is longer. Let's say it took 1.2 seconds instead. What would the force be like? So go ahead and pause the clip and do this. And then when you're ready to check, you can hit play to continue. All right, so same change in momentum, but here the force is much less. And if you remember, the change in momentum is due to both, right? We're looking at force and time. So if you can extend that time, for instance, with car crashes, if you can, have bumpers that are, cushiony, where it increases the amount of time of impact, you can have less force. And so, we looked at a lot of that in your junior year, looking with safety with that. So these two clips, the first one is that Mack truck that I showed you guys, back last year, where, it hits a concrete wall. It's a remote controlled crash, it hits, and the time is very short. And so the force is very large, versus the one where that car hits the water cans and the time is extended, so the force doesn't have to be as much for the same change in momentum. All right, so let's go ahead and try this one here. This is an object moving 120 meters per second. There's a force in the same direction as the velocity, and we want to find out what's the new velocity of the object. So go ahead and pause the clip and give this a try and see if you can remember what to do here. And when you're ready to check, you can hit play to continue. All right, so if you remember like with a position time graph or velocity time graph, if we want to know how far the car goes, v equals delta x over t, we can multiply the velocity times time and get the area. And the area, because V times T is delta X, it'll give us what we want. So in this one here, we have force on the y-axis, time on the x. We're multiplying the two things. Therefore, the area itself here will give us the change in momentum. That area is 125 kilograms meters per second, 1/2 base times height. We know the change in momentum, and therefore we can find what the final velocity will be. It should be 224.17 meters per second.